This is going to be the first video that deals with functional groups. In organic chemistry, an important concept that we're now moving into are the different types of molecules based on some of the things other than carbon and hydrogen that appear in the molecule. And so these are known as functional groups. So first of all, if we did define functional group, how would we define that? Well, so functional group then, group of specific atoms within a molecule that are bonded in a predictable fashion, that's because of the atoms involved, but are responsible for the characteristic reactions of that molecule. That is to say, a certain functional group is going to mean that molecule always reacts in a similar fashion. It's very predictable. And the functional group reacts in the same way irrespective of the size of the molecule it's a component of. So you could have an ethane with a certain functional group on it, and it will react in exactly the same way as a decane with the same type of functional group. So we really look to functional groups to talk about reactivity of a molecule, because the reactivity is going to be due to the functional group. Here are some just some examples of functional groups. And so even a simple alkane can be considered to have a functional group, and typically we look at that as the hydrogens. So a common reaction with alkanes is that a hydrogen gets displaced or substituted off the alkane chain, and you put something else on. Alkenes, the functional group then is really this double bond. So the reactivity in an alkene is usually around the double bond. Here is a fluorine attached to a hydrocarbon chain, so that fluorine is the functional group. Here's another functional group, C double bond O. Here's C double bond O as well. Now, these two functional groups are actually different. They're called something different because of the position of the functional group. And finally, here's another one. You might recognize this one. C double bond O, bond, single bond O with an OH attached at the end. So that is, again, a specific functional group. That's a carboxyl group, so that's carboxylic acid, which you may have heard of. All right, so let's start looking at functional groups, and the first one we're going to look at is the single bonded functional groups, and specifically a group known as the haloalkanes. So haloalkanes have, as it suggests, a fluorine, a chlorine, or a bromine attached. So those halogens are going to be bonded onto the parent chain. So you have an alkane, alkene, alkyne chain with a bonded halogen. So halogen is always considered as a branch of the carbon chain. So just a couple of examples. Here's one. So there's my carbon, and there's my halogen attached. So that's a 3-chain halogen. Attached to carbon 2 of that chain is this halogen, and that is probably a chlorine. Here's another long chain hydrocarbon. So this is an alkene. So here's my longest continuous chain. And there's the branching. So we have a fluorine attached on this carbon and a bromine attached. So those are both examples of alkyl halides. Let's look at the nomenclature for alkanes. It's really quite straightforward now that you know the system. The main thing to remember, the parent molecule is going to be an alkane or an alkene or alkyne. So as I said, the halogens are always branches. So the name of the halogen that's attached, a chlorine for example, is going to be abbreviated to chloro. So it's not chlorine on a halogen, it's a chloro. And it becomes a prefix on the parent molecule. And if necessary, and this is commonly the case, the position of the halogen has to be indicated. Multiple branches are dealt with accordingly. And so multiple branches, how do you deal with those? Prefixes and list alphabetically. So let's have a look at some haloalkanes. So here is my 2-carbon chain. We're going to number accordingly. 1, 2. So that's an ethane, and what I have attached to my ethane is this bromine branch. So that becomes a bromo. So I'm just going to call that bromo ethane, and I don't need a number. I don't need the 1 for bromo, because if I move this bromo over here, this becomes carbon 1 and that becomes carbon 2. So I don't need the number in that instance. How about this one? This looks like a pretty crazy molecule. So let's start looking at the longest continuous chain. So I'm going to start here because it's an alkyne, so that takes precedence. So there's the chain, down that way, up that way, there we go. So there's my longest continuous chain, and that's 1, 2, 3, 4, 5, 6, 7. So that's a heptyne molecule, or parent chain. And here are my branches. I have a fluorine attached on carbon 4, and I have an ethyl branch on carbon 3. And so that's going to be 3 ethyl, 4 fluoro, hept, 1 ine, because it's an alkyne and we have to indicate the position of the bond, because that bond could be elsewhere in that molecule. But so there's the 3 ethyl and the 4 fluoro, so alphabetically E and F. How about drawing? Well, again, the system takes care of the drawing. It should be pretty straightforward. Hex 3, I draw that first. There's my 6 carbon chain, and on carbon 3, 1, 2, 3, I have the start of a double bond. So there's my hex 3-ene. On carbon 2, I have an iodine, iodo, and on carbon 4, I have a bromine, or bromo. And now I can add hydrogens. Carbon 2, or this carbon, yeah, that's carbon 2, only has a single hydrogen. Carbon 3 only has a single hydrogen. Carbon 4 is saturated, so there's no hydrogen in carbon 4. And there we go. So there is 4-bromo 2-iodo hex 3-ene. Para-dichlorobenzene. If you remember benzene, there's my benzene. Aromatic form of the benzene. Para, that, if you remember, means opposite. So para-dichloro. So there's para-dichlorobenzene. It could also be called 1,4-dichlorobenzene. One other thing you should know is classification of haloalkanes, and this is pretty straightforward in terms of a classification that tells us something about the actual structure just based on classification. So we talk about primary, secondary, tertiary haloalkanes, and how we identify this. It refers to the number of carbon atoms attached to the carbon atom that is bonded to the halogen. So let's look at this by way of example. So here is my haloalkane. Here's my functional group. Here's my halogen attached to the carbon. So how many other carbons is it attached to? Well, it's only attached to one other carbon. Here it is. This carbon here. No other carbons attached, so that's known as a primary haloalkane. And this is, if that's a bromine, is just bromoethane. So bromoethane is a primary haloalkane because the carbon bonded to the halogen is bonded to a single other carbon only. Well, let's look at the second example. So here's the carbon bonding the alkane, and it's bonded to 2 other carbons, this carbon and this carbon. Those aren't numbers, by the way, I'm just indicating how many there are. So the carbon containing the halogen is bonded to 2 other carbons, so that's a secondary haloalkane. And in this case, if this is chlorine, that would be called 2-chloropropane. 2-chloropropane. And so finally, tertiary, hopefully you've seen the way it works. There's the chlorine bonding, or carbon, sorry, bonding the functional group of fluorine in this case. And how many carbons is this bonded to? 1, 2, 3. So it's bonded to 3 other chlorines. So that's a tertiary haloalkane, and that would be called 2-fluoro, 2-methyl, butane. 2-fluoro, 2-methyl butane is a tertiary haloalkane. So that's how you classify haloalkanes. And again, this classification will come back and show itself when we talk about reactions of haloalkanes. Finally, I want to talk about halogens or haloalkanes and polarity. Polarity is an important concept in all organic molecules because it's going to dictate some physical properties that we're going to talk about. So haloalkanes are fairly easy to sort out, at least 2 of them. So certain halogens, namely fluorine and chlorine, have reasonably high electronegativities. Therefore, a carbon-fluorine bond and a carbon-chlorine bond, both of those are going to be polar, known as a bond dipole. Depending on the geometry of the molecule, you can have a molecular dipole. I'll talk about that in a second. That is a polar molecule. So because of the polar bond caused by the carbon bonding to the halogen, you end up with a polar molecule. And as we're going to talk about later, molecular polarity really does affect physical properties. So first of all, let's just consider methane. So there's methane. So that's a carbon, and it's bonded to a hydrogen. So that's a carbon-hydrogen bond. So a delta En for a carbon-hydrogen bond is, I believe it's 2.5 for carbon minus 2.2 for hydrogen, which is 0.3. So that's a non-polar covalent bond. So clearly that non-polar bond doesn't help with polarity. None of the bonds are polar, so methane is in fact a non-polar molecule. There's no molecular dipole there. Well, let's look at another one. So this is fluoromethane. So fluoromethane has this carbon-fluorine bond, and the delta En for that is 4 for fluorine minus 2.5 for carbon, 1.5. So that is a very polar bond. That's a polar bond, and because of the geometry, because of the arrangement of that polar bond and these other non-polar bonds, you have a polar molecule. And so we can show this molecular dipole this way. This is the delta negative component. Down at this end is all delta positive. So that's a polar molecule. So one would predict, based on the polarity of the molecule, that the physical properties are going to be based on this polarity, and they're going to be different than the physical properties of methane. So there you have it, an introduction, first type of functional group, the haloalkanes, and halogens bonded to carbon on the chain. And so we've talked about the classification of haloalkanes, and we've talked a little bit about bond polarity and molecular polarity caused by the bonding in the functional group. And this is what we're going to focus in on for the next little while. So that concludes this video.